The last section of this chapter is about the kinematics equations and how to use them. So we've already done all the graphing stuff. We've done graphs qualitatively and quantitatively. So here we're going to learn how to solve story problems using the 5 kinematic equations that I'll explain here in a second. On this chart, you see the 5 kinematic equations. So these are the top 5 here. Anytime you have a problem involving acceleration, you'll use one of these 5 equations. If you have a problem that's involving a constant velocity, that's when you have to refer back to our buggy lab equation. So you can only use this blue equation when there's constant velocity. So the first thing you do when you see a story problem is determine what kind of motion you have, constant acceleration or constant velocity. So what this chart does is it's a quick way to help you figure out which equation that you need to use in a given situation. As you practice using these equations, it'll get a little easier for you, but especially as you start out, this will help you out. You will, by the way, have this exact same chart given to you on any quiz or test that we have where you need to use them. So if you learn how to use it, it'll help you in those situations. So here's how it works. On any given story problem, they will give you 3 out of 4 variables in a problem. So they'll give you 3 numbers, and then they'll ask you to solve for the 4th. So in that, if you notice, there's actually 5 different kinematics variables. So for every problem, there will be one variable that they don't give you in the problem, and they don't ask you to solve for. So that's what you call the who cares quantity. So who cares about that variable? If you can figure that out, then you can look back on this chart and say, oh, if they didn't give me X, they didn't ask me about X, that tells me wajam. I'm going to go ahead and use this equation. So that's what the point is of this chart, and you'll use it a lot in this class. So take a little time, make sure you're comfortable with it. The next thing I have for you is a basic problem-solving strategy whenever you come across a kinematic equation. You do not have to write down step for step when you do a problem, step 1 this, step 2 that, but you should be following the same basic path through any story problem that you have. When the story problems start out in this class, they'll be fairly easy, and the easy ones you may think, oh, I don't have to do all this. But as the problems get more challenging, you most definitely will. So don't be skipping it. You can't skip it and be able to get away with it long term. So here's my quick problem-solving strategy. You can read it, but let me just highlight a few things. Always start with a sketch. Doesn't have to be art, can be if you like, but you need something that can show you what's going on in the problem. Number 2, choose which direction will be positive. Normally to the right is positive and up is positive, just like it were a regular XY graph. However, you will find situations where it's more convenient to switch that. So you do get to decide which direction is positive, which one's negative. You can always solve problems either way as long as you're consistent throughout the problem in that direction. Number 3, list your knowns and unknowns. Some of you will think that you don't need to do that, and again, it will get you in big trouble when you get into harder problems. So always, 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 no matter how easy the problem is, list your knowns and unknowns. Always put the units in as well. Number 4, check to see that the units are consistent. So if they give you kilometers per hour and then ask you about the time in seconds, then you know you need to convert something. So you need to make sure your units match. In our early problems, they will match. As the problems get harder, they won't. Number 5, pick the kinematic equation you want to use. That's using the who cares equations. Number 6, you're going to put the numbers in and then go ahead and solve it. Number 7, check to make sure your answer is reasonable. Don't just write down whatever your calculator gives you, because your calculator might give you the wrong answer if you've made a typo or something like that. So you want to make sure that the number that you write down is actually reasonable. Here's a couple tips and tricks for story problems. A lot of times in a story problem, they will use words that will actually be telling you a variable. So here's a few examples of things to look for. They might say, a car starts from rest. That means the initial velocity is 0, even though they don't come out and say VO equals 0. You can figure it out from reading the problem. A car slows to a stop. That means V is 0. Or on number 3, I'm actually going to save this discussion for free fall. But if you know something is falling off on its own, it's not it's not being launched by a rocket or you have a rocket pack on it. Once something is traveling through the air on its own with nothing pushing or pulling it, then gravity is the only thing acting on it, and gravity always has the same acceleration, negative 9.8 meters per second squared. In the same way, if something goes up and then falls down, right at the top of that, it will have a velocity of 0 meters per second, and that can be useful. We'll see more on this third example in later chapters. So here's a couple example problems of story problems that you'll see in kinematics. I'm not going to take the time to read the whole question to you because I'll run out of time on this video. So if you need to, pause the video, read the question so you know what I'm talking about. So I'm going to follow all of the problem-solving steps that I mentioned before and go through each of them. You don't need to label step 1 on your own problem-solving, but you do need to follow this basic process. So the first step is to draw yourself a picture. Since I'm doing this on a computer, I can make a real nice little picture, but yours can be any type of a sketch that you can make. So here's my computer-generated diagram that I made. So you have the 10 meters per second at the wall, 8 meters per second back. Just by drawing this sketch, this should actually tell you something. There is a change of direction in this problem. Because there's a change in direction, the sign is going to be important. Notice they didn't tell you the sign on 10 meters per second or 8 meters per second. They just gave them to you both as positive. But in reality, if you use this in a problem, you can't make them both positive because they're in opposite directions. So looking at the sketch is one way that you can see things like this, that here the 8 is going to have to be negative. And I kind of skipped ahead just a little bit. I have to decide which way's positive, which one's negative. So my step 2 is going to say that anytime to the right is positive. And that's just kind of a general, usually to the right is positive and up is positive. So we're going to say this direction is positive, just like it's a number line. This direction would be negative. Okay. When I do that, I'm going to say 10 there is positive and my 8 is negative. Does that matter? Oh yeah, because if you don't have those signs on there and you actually solve the problem, you're going to get the wrong numerical answer. So it's really important to make sure you have the signs correct. So in step 3, you have to list your knowns and unknowns. Again, never ever skip this step. It's really important. So you know your initial velocity is 10 meters per second. When you see the units, that tells you that it's a velocity. You know your final velocity is 8 meters per second. Very important that it has to be negative because it's going in the opposite direction. The time was given. The question is, what's the acceleration? So that's what we're looking for. So notice they gave you 3 numbers. They ask you about a 4th, and there was one variable they didn't give to you and didn't ask you about. That's the who cares quantity. So the who cares quantity, if you refer back to your sheet, the little chart is going to tell you which equation that you need to use. So step 4, you look at your units. Here, they all have meters in it and they all have seconds in it. If they had given you a time that was in minutes or something like that, you would know that you would have to convert it so that they all match. So in this case, the units all match and we're good to go. Our early problems will mostly match for units, but as we get a little better at solving these equations, we'll have a little more of a challenge with that. So don't stop looking for it just because the early problems don't have a lot of conversions. We'll get to that in a little bit. So step 5, we figure out which equation we have. Again, this is the who cares equation for x. So it's got all of the variables that they gave us. It's got the one that they asked us about. It just doesn't have x. So that's our equation. Now all we have to do is put numbers in it. So here we went ahead and put numbers in it, and I went ahead and solved it. And silly conversion program here doesn't line them up. That's annoying, but that's okay. So I put my numbers in. I go ahead and solve for acceleration, and I get an acceleration of negative 1,500 meters per second. It's a pretty big number. So that might get you to look at, is that answer reasonable? In this case, a lot of times you'll have answers that are velocities or times, and you'll have a better sense of if they're reasonable or not. But in this case, it's a little harder because it's an acceleration and it's a big number. But here's what you can say, is that you have a pretty big size change in velocity, not huge, but 18 meters per second. It's a decent size change in velocity in a really, really, really small time. So it's the really short time that makes a big difference in this acceleration. Due to the short time, you can say, yes, this answer is reasonable. So let's look at one more example problem on this video. So again, take a second, pause it, read it, make sure you understand the question, and then we'll start step one, which is to draw a diagram. Actually, that looks just like my car, pretty much, except my car's all red. The flames are nice though, good touch. So I have my car, it's going to hit the puddle and it's going to come out slower. So there's my picture. On my step two, I need to describe which direction is going to be positive. So we'll say to the right is positive. That's a general standard, although there are times when it's convenient to change that. In this case, this makes the best sense. Step three, I'm going to list my knowns and unknowns. So I know the distance of the puddle is 5 meters. I know my initial velocity is 20 meters per second. I know my final velocity is 10 meters per second. In this case, there's no change in direction, so the 20 and the 10 should have the same sign. So they actually asked me two parts in this question, and that's fairly common in kinematics problems to ask two different things. So first, they ask you about acceleration. So that's my question for part A, which means that for part A, I don't care about time. So again, that tells me which equation to use using my who cares sheet. In part B, they asked me to solve for time, so we'll have to look at that separately. So first off, we're going to use T for our who cares. Step 4, we don't have any problems with units here. Everything's in meters or meters per second. So now we can go ahead and put our numbers in our equation and solve. So the who cares equation for time is the v squared equation, so we'll use that one. And I'll go ahead and put my numbers in. So I put my numbers in, I use my calculator, and I go ahead and solve it. If you ever struggle with getting the right number out of your calculator, you should take a second and punch this in your calculator and make sure you can get the right answer, because that's pretty important. It'd be a shame to do all the work and not be able to put it in your calculator correctly. Now, so that was all just for part A. So then I went ahead and worked through part B separately. Now, as an important tip, there are times when you're forced to use an answer from part A and part B, but in this case, they gave us enough information that we don't have to use our part A answer. So we're going to say that acceleration is our who cares for part B. If we do that, we come up with another equation that doesn't have acceleration in it. The reason you do that is, let's say you made a mistake in your calculator or whatever, you get the wrong answer for acceleration. You don't want to use that number in part B because you'll automatically get the wrong answer. So it's always best, if you can avoid it, to not use your part A answer for part B, because it's possible to get part B right even if you've missed part A. So there's my who cares equation for part B. So I can go ahead and put my numbers into the equation and solve for it, and when I do that I get 0.33. So step 7, is that a fairly reasonable answer? I would say yes, because it's not, it's not an unusually large time here. That's a short amount of time, but it's not super duper small or super duper big, so it looks okay. Same thing for the acceleration, 30 meters per second squared. I think it's harder to have a good sense of acceleration values when you calculate them, but you can say that 30 is a fairly average number. There's nothing weird about that. If you compare for acceleration, sometimes it's convenient to compare it to the acceleration due to gravity. So the acceleration due to gravity is 9.8 meters per second squared, and that's what they would call, in roller coaster world, they would call that 1g. So this is the equivalent of about 3 g's of acceleration, which you can get that on a good roller coaster. So that's not a strange acceleration, that's fairly reasonable. So that's it for this video. We've looked at 2 of the 3 examples. I'll do a separate video for example 3. So we'll work on problems on this in class, and you'll have a chance to work through a few on your own.